In this session, we will build a linear regression model using PyTorch. First, let's understand what a linear relationship is. This equation defines a linear relationship between input x and output y. In other words, the slope and intercept determine the linear relationship between x and y. For example, a equals 0.5 and b equals 1. Then, we have y equals 0.5x plus 1. If we input x equals 0, we get y equals 1. If we input x equals 2, we get y equals 2. If we input x equals 4, we get y equals 3. And so on. As we can draw a line to show the relationship between x and y, we call it a linear relationship. The intercept is the y value for x equals 0. The slope is how much y changes when x increases by 1. Real-life data may have noise, even though the underlying relationship is linear. Here, I've added random values to the original line, y equals 0.5x plus 1, to simulate noisy data. Even though we have noisy data like this, we may assume x and y have a linear relationship and try estimating the slope and intercept. This is the question of a linear regression problem. In other words, we want to find a and b that best describe the linear relationship between x and y. For example, we may try random values for a and b to find a line that best fits sample data points. I use notation like a hat and b hat, which means they are our guesses for the best a and b. So, y hat means an estimated value of y given a hat and b hat. If we are patient enough or lucky, we might find a solution eventually. But there is a better way, which we'll learn later on. Right now, we need to understand what best fit means. How do we know if we find the best fit solution or not? The best fit linear solution minimizes errors between the line and sample data points. We already know the answer is a equals 0.5 and b equals 1. So, the best fit line is y equals 0.5x plus 1. But let's suppose we don't know the answer and want to estimate the best fit solution a hat star and b hat star. First, we need to define what an error is. An error is a distance between sample point y and an estimation of y for the same x value. Blue vertical lines are examples of errors. Mathematically, we calculate an average of squared errors, which we call mean squared error or MSE. MSE is always 0 or a positive number. MSE becomes larger when our estimate fits sample data points poorly. Therefore, the best fit solution should have the smallest possible MSE. In other words, we want to adjust our estimates of a and b to minimize MSE. We want to adjust a hat and b hat to minimize MSE. We need partial derivatives of MSE with respect to a hat and b hat, so that we can adjust them in the direction to reduce the value of MSE. So, what is a partial derivative? A partial derivative of MSE with respect to a hat tells us how much MSE changes when increasing a hat while keeping everything else fixed. If it's positive, we should decrease a hat to reduce MSE. If it's negative, we should increase a hat to reduce MSE. Similarly, if the partial derivative with respect to b hat is positive, we should decrease b hat to reduce MSE. If it's negative, we should increase b hat to reduce MSE. A gradient is a vector of partial derivatives, so we want to calculate the gradient of MSE with respect to a hat and b hat. As we'll see later, we can use PyTorch tensors to calculate gradients. For now, let's remember the gradient of MSE tells us in which direction to adjust our parameters. Let's call a hat and b hat collectively parameters. Also, let's call MSE as loss function. In deep learning, we often use these terms. With PyTorch, we use an optimizer to adjust parameters. It uses the gradient of a loss function to increase or decrease parameter values in the directions to reduce loss value. A learning rate tells the optimizer how fast or slow to apply the changes. We covered enough ground to perform linear regression with PyTorch. Let's start a demo with some PyTorch coding.